All right, so next class we have an exam, right? And I posted the practice problem, but I want to show you another one. Another practice problem that you may want to look at. So this is the JUMP website, okay? And practice problems that I was posting, they come from the JUMP library of cases that they built, okay? So go to jump.com just to find that thing, right? And after that, there is a link right there that says Learn JUMP. And there is case study library. Okay, so in Learn JUMP, there is a link to case study library. So a lot of practice problems and cases that I posted this semester were actually coming from case study library. So that's everything that they have. That's quite a lot, actually. And what I typically do is I sort them by the analysis type. So what we did this semester is right here. We did predictive analytics, okay? So the one that I want to point your attention to is Titanic. Remember we did Titanic at the beginning of the semester, predicting who will survive and who will die. What did we do for the Titanic example? I believe we did the classification tree, right? We said that biggest predictor, whether you die or survive, is what? What's the biggest variable that predicts your chances of survival? Gender, right? Most males will die and most females will survive in the crash of Titanic, okay? So that was our first split, right? Could we do it using logistic regression? Absolutely, right? Because at the end of the day, you're predicting yes, no type of response, right? Target variable. So logistic regression is the natural choice as well. And that's what this example does. It takes the same exact problem, Titanic passengers, and it uses logistic regression. So what I would do is go ahead and read through that case, okay, before Monday, right, on jump.com. So it has the PDF file that is the solution, essentially, right? So they go through nice description of the problem and then visualization. And after that, they also have the data set that comes with that. So that's a nice practice, okay? Now, what I wanted to do today is to show you, we just finished clustering, right? And the reason why we did clustering was what? I hope to cluster similar observations together so that at the end, I will be able to build a separate model for each one of them, right? Hopefully my model for each separate cluster is going to be better than the original model, right? Because clusters are similar observations, similar cases, right? So if I cluster similar cases, then probably the model that I will be able to fit will fit better. Simple as that. And you know what? For that, we're going to use our good old friend price of the vehicles. Remember we did the car prices, right? Toyota Corolla, I believe that file was called. Do you see the file Toyota Corolla in the list of the things out there when you start to jump? Is it still on the list? It is? Yes, agree. No? Can you find it on the list? Yep. Okay, go ahead and open up the file Toyota Corolla.jmp. It should give you this, right? Okay, so how many observations? Everybody sees that file? Okay, cool. How many records do we have? 1,000 records, right? So it's small data, I told you before, right? Everything that we're dealing with in this class is small data, technically speaking. Okay, so let me go ahead and use the entire data to build my model, right? So I'm not going to separate cars into clusters right now. Okay, I don't even know how to start doing that, quite honestly. Some of them are old, some of them are fairly new, right? Low mileage, high mileage, horsepower is all over the place. I don't know how to even start. Okay, so I'm going to build a regression, right? Remember what did we try to predict? What was our target variable? Price, right? We were trying to model if we can predict the price of the car based on all other things, right? Well, let me do this, okay? I don't quite know how to use, how to cluster things based on categorical variable. Right now, my predictors is a mixture, right? It's a mixture between the continuous variables and categorical. I can find distance between continuous points, right? with points x1, x2, x3, x4, and y1, y2, y3, y4, I can apply the like Euclidean distance formula and find the distance between the points, right? But what if some of my measurements are not numerical? And it becomes kind of a little bit mixing apples and oranges together, right? So how about that? I'm going to skip all the non-numerical predictors. Leave only continuous predictors, okay? That would be age, mileage, skip the fuel type, horsepower, skip metallic and automatic, and select the rest of them. So only numerical predictors, okay? And that becomes my model effects. So I'm just going to show you how I can use clustering to maybe build a better model, okay, for predicting the price. All right, so I'm going to run the model, and there it is. Okay, it says that the biggest predictor, the most important predictor is what? Most contributing. Right there. Age, right? Age of the car is going to be the biggest one. Amazingly not mileage for some reason, right? Mileage is still, by the way, according to my p-value, mileage is still significant, right? All of them are significant with the exception of what? Number of doors seems to be not contributing, right? P-value is large. And also, what's CC? Is it like engine volume, cubic centimeters in engine volume, something like that, right? That's also not important. But age, horsepower, mileage, weight, and quarterly tax are important. Okay, let me be simplistic. Okay, I'm not going to get overly complicated on this data set. How do we measure how nicely my model fits into the data? R squared, right? Well, let's use R squared. Summary of fit, right? Here, my R squared right now says 0.8625. Is that a good model or is it not so good model? Pretty darn good, right? Basically, the variables that I've selected, they explain about 86% of what's going on with car prices. PDN, right? No, PDG. Pretty darn good, right? Only what? 14% of variation is not explained, right? That's a good model. Okay. Well, if it's good, like what's the rule of thumb, right? If it ain't broke, don't fix it, right? Well, let's try. Okay, it's not exactly broke, but let's try to fix it even more. Okay, so I have to remember that number. 86.25% of variability is explained by my model. All right, and now let me go ahead and do the clustering analysis. Okay, and for that I'm going to use really any of them, right? So let's take a look at how we can slice the data using, and that's where it becomes an art rather than science, right? Should I use k-means or should I use hierarchical clustering? No idea, right? Well, let's try k-means. Okay, k-means right there, and I'm going to do the same thing. Okay, I will try to cluster observations together first, right? Judging by their numerical characteristics, and I actually played around with this data set before the class, right? So let's do this. I'm going to include all my variables, all numerical variables, right? Because I used only numerical variables to build my regression, so let's do that. I'm going to include price, age, mileage, horsepower, and the rest of them, right? And skip categorical. So let's just put it in. And it's going to be weird, I got to tell you, a little bit. Well, you'll see. So here's my clustering, right? And let me be simplistic, for crying out loud, okay? So I'm going to use 3 clusters, just that, okay? Remember our discussion that if you have too few clusters, it's not cool because clusters become too broad, right? They include observations that are not necessarily similar. If there are too many clusters, we're kind of splitting hairs, right? Clusters can become very close, almost indistinguishable, right? All right, I don't want that, so let's use 3. Okay, now first thing that jumps at you, tell me. This is the result of the clustering. I have 1, 2, 3 clusters. Anything looks weird to you? Unusual?
There's like a large difference in all the numbers. Like the first cluster is 1, 2 is 198, and the third one is all that.
Exactly, right? One of the clusters is actually not even a cluster, it's just a point, right? Do I want to use that as a cluster? No. It's kind of weird, oddball case, right? some car. I don't even know why it's a separate cluster, right? Why it just never joined anything else. But obviously, I'm not going to even look at that, right? How can I build a model with the sample of one observation? I can't really, right? All right, so let me go ahead and use the biggest cluster first. Okay, so 801 observations. And this is actually what JUMP can do for us, okay? When I select the cluster in this output, remember when we started this semester, we said all windows are interconnected. You select something in window 1, it affects window 2, right? Let me go back, so 801 observations, right? If I go back to my data set, look at that, it says selected 801 observations. So when I selected the cluster, I actually highlighted 801 entries, okay? And let me I want them to be separated, right? I want to build model just for them. That's it. So how about that? I'm going to right-click on the word selected, and do you see there is an option that says data view. Let's select data view. What it does is it takes 801 observations that I selected and kind of separates them into its own data set. Is that cool or what? So I can easily filter out whatever records I need, okay? And that's what I just did. That's my biggest cluster, right? And let's do exactly the same thing, all right? I'm going to go to the fit model. I want to build, again, regression analysis, right? Just for this subset of points. And maybe this model is going to be better. I can actually use recall button. Okay, it will say, yeah, you're going to predict price against age, mileage, horsepower, and all this other stuff. Okay, fine. And I'm going to run the model. And again, I'm looking just at one number, right? How well my model fits the data. Okay. What do you think? Is it better or worse?
Worse.
It's worse, right? What was it? 86.2%, right? And now I went down to 62.7%, right? Not exactly the direction I want to go. So that kind of sucks. Well, let's see what happens on the smaller cluster, right? So I'm going to close that one and the data as well. I don't need that anymore. And let's go back to my clustering window, right? I'm going to do the same exact thing. Pick cluster number 2, 198 observations, right? That's smaller cluster. And let's go back to my data set right here, okay? All right, this one, and it says, you have selected, my dear friend, 198 observations, which is what I wanted, right? That's my second cluster. Again, same thing, I want to separate these numbers, these values, into its own data set. Data view, kaboom, all right. And I want to fit another regression just into these points, right? So let's do that. I'm going to go fit model, again hit the recall button, just so that I don't have to click and drag and all that. All right, click the run. Here is my model. Is that better or worse than my original?
Worse.
Still worse, right? I did clustering, right? And I took cluster 1 and cluster 2, and both models were actually worse than the general model. Is that what I want, really? No, right? It sucks, okay? So, oopsie daisy. So, all this stuff that I told you was just a bunch of crap, right? About how we separate things into the clusters, and then clusters are similar, so therefore model will be better. That kind of contradicts it, right? A little bit, okay? So, what does that tell you? The results of data analytics are not guaranteed, right? You may find better model, or you may not find a better model. Heck, in some cases, you do the data analytics, there is no model at all, right? You're trying to predict some weird stuff based on some measurements. You hope for the best, right? You build a model, and it turns out that none of your variables are significant, and the accuracy is really bad. Misclassification rate is high, so your model is pretty bad, right? So, does that mean that all the hope is lost in this case? No, I just may want to do things differently. And here's what I did. Let me show you, okay? So let's close out everything, all this analysis and the clustering as well, right? Here's what I did. I was kind of playing around. And that's what data analytics is, okay? The models that you're building essentially are algorithms, right? They're fairly standard. So I don't remember if we discussed it this semester in this class, but the data analytics, the majority of time how do you think the data analysts spend the majority of their time? What are they doing? Do you think they're building models and running regression analysis and evaluating R-squares? No. It occupies approximately 15% of their time, because most of that already is automated by the software, right? You just plug the right data into the software, tell it what to do, and it will do it for you in no time, right? Then you may exclude some variables, modify some other variables, tweak things around. That occupies about 15% of the time. What occupies about 80% of their time? Data preparation, okay? These data sets are nice, clean, and ready to go, right? Nothing is missing, no weird values, everything is nice, okay? In real life, you don't get that, okay? Some data is going to be outside of your organization. Like you need to find it somewhere and somehow put it as a column right into your data set. Some data will be duplicated, some things will be missing, some things will be weird. So data cleaning is what takes most of the time, all right? Anyhow, here's what I did. Let's do the analysis again, right? That means clustering. So let's go to Analyze, Clustering, and still I'm going to be simplistic. I'm going to use k-means, all right? Click. But this time around, I'm going to cluster my independent predictors. Remember, the previous time when I clustered things, I selected all of numerical columns, right? Including the price. Price is what I'm modeling, right? So essentially I'm saying, put things with a similar price together in the data set, right? Well, and other things similar as well, right? This time around, what I'm going to do is I'm going to say, leave the price out, but pick age, mileage, horsepower, and the rest of them. So I'm going to try cluster things based on my independent predictors. Can I try that? Sure, right? Whatever works. If that gives me a better model at the end of the day, yeah, let's go, right? Okay, so I'm going to add them to the columns and click OK, and still stick with 3 clusters. Let's just be simple, right, about that. And then I say go, all right? Now, note that things are kind of looking similar, right? In my previous case, remember, one observation formed its own cluster, right? Still the case, right? There is an oddball car somewhere in my data set which just doesn't want to cooperate with other cars, right? It looks freaking different. Whatever it is, okay, I don't even know. You know, heck, just out of curiosity, right, what is it? Let's make into data table, right? That's what we want, make into data table. This is the only, no, hold on. That will create the same thing, right? No, that's not what I want. I selected this cluster, so I go back to data and it says one row is selected. Yeah, let's look at that at data view. All right, this is the oddball car, right? It has the price of 18,950 euros, 25-year-old. That's probably what it is, right? Do you expect to pay 18, almost 19 euros, which actually translates into like $21,000 for a 25-year-old car? There is something special about this car, right? It just doesn't match because the age and how large is the mileage? Mileage is actually also pretty low, right? That's unusual. Old car with low mileage that costs enormous amounts of money. I don't know, maybe it was owned by David Letterman or something. Like there is something special about this car, right? Why a 25-year-old car is worth so much? That's probably why it was separated into its own class, right? Just doesn't conform to any other behavior. Okay, so we're not going to look at this thing, right? But I'm going to look again at my clusters 1 and 2, right? Because they seem to contain a lot of observations. So let's start with bigger cluster, right? Because bigger is better. All right. You've seen that cartoon, right? No? What cartoon is that from? It's raining with the chance of meatballs. Raining. Cloudy and with the chance of meatballs. Right? The mayor of the city, right? Here's what I heard. Yada, 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 blah, 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 science, bigger. And bigger is better. So, let's take a bigger and better cluster, right? Okay, and let's go and separate that cluster into its own group. So let's look at the data view, right? Separate these 877, is that right? 877, yeah, 877 points into its own cluster. And again, let's see it in what type of model? Multiple regression, right? So I want to see if that cluster is better. Fit model. And again, I can use my magical button recall, which will put the same configuration as before, right? And then I'm going to just run it. Predicting price based on other numerical characteristics. Click run. Here is my model. And again, I'm being simpleton here, right? I'm just looking at one thing. That would be R squared. Is that a better R squared? It is, right? What was my original when I just built the model for overall, the whole thing? 86.2, right? This one is 87.27. So is that a drastic improvement? No, right? It's slight improvement, but in the world of statistics, still can be important, right? If I can get a better model, that still counts. But hold your breath, right? Because I'm about to show you another cluster, and that will blow your mind away, okay? So I'm going to go back to my clustering analysis and pick smaller subset that it selected, right? With only 122 observations. And let's do exactly the same darn thing with that smaller, but still beautiful cluster, okay? So I'm going to go back to my data table with data, with second cluster selected right there. I will put that into the data view. So what have we in the second cluster? There it is, 122 observations, and I will do exactly the same thing, okay? Fit the linear regression. So fit the model, recall, and then run it. And let's take a look at the R squared. Is that beautiful or what? It is, right? This one fits nearly perfectly, right? Well, I shouldn't say nearly perfectly. It's 92%, but it's better than anything I had before, right? So it's a matter of basically messing around with models and trying different ways, right? You never know what's the best way to cluster things. We picked k-mean with 3 clusters, right? Well, one of them was cluster of just one car, unusable, right? So we had to discard it, right? Could it be that I need to use 4 clusters instead of 3? Could be, right? You never know. Or I could go with hierarchical clustering, right? Not k-means, but hierarchical with 3 clusters, with 4 clusters. Who knows, right? So in other words, as a data analyst, that's basically how data analyst job looks like, okay? Here's your data set. Try to create as much information out of that as possible. And then you start experimenting, right? Messing around. Try cluster one way, another way, with 3 clusters, 4 clusters, 7 clusters, okay? Build the models, compare them against each other, right? That's basically what Christmas is all about, okay? Any questions, ladies and gentlemen? Well, we still have about 17 minutes, right? So we're pretty much done with clustering. So will you be able to do something like that on the upcoming exam? No? Let's not even try, right? Okay. Well, I have to let's have some fun, right? Let's have some fun with. Well, we're about to start probably our last topic. Maybe there's going to be one more, depending on if we have time or not. Well, let me tell you. Whoa, is that our previous lecture? When we did the clustering of the rows, right? And also, we discussed the, what's it called? Principal component analysis, right? When you take the variables and create linear combination out of them, right? Making model more sophisticated. Okay, anyhow. Artificial intelligence, ladies and gentlemen, AI. Did you see, by the way, yesterday at 11 o'clock, did you see the presentation? Nobody looked at presentation? Elon Musk? He is planning to build the truck. He's taking on the trucking industry, right? The electrical truck. They presented not only truck, but also like super sleek roadster car, right? Probably expensive like hell, but it can go from 0 to 60 in 1.8 seconds. It's enormous, yeah. Trucks that he presented yesterday, I don't know how much they're going to cost, quite honestly, because the battery alone, you understand that in electric, what's most important, what most expensive component of the electrical car? Can you guess? Battery, actually, okay? Battery is, most of the batteries that we use as a humanity are lithium batteries, okay? And lithium is actually a rare element. So there is a technological limitation how much we can go, right, on lithium. But battery is the most expensive thing in the car, really. So the trucks that he presented yesterday, probably the battery alone for each of these trucks is going to run, I'd say, $100,000 in cost, just the battery itself. And then you add more stuff on the top of that, all the automation, and it's actually a pretty cool thing that he showed. It has 4 independent motors. So therefore, the truck is virtually 100% reliable. If the motor goes out, it can still move. So if you're in the middle of nowhere and motor gets busted, normal truck will just, that's it, you're staying there, right? That will keep going, and fairly impressive. The range also was good, actually. He said, range is one of the problems, right, with electric vehicles, right? Because how far the car can go on one charge, that's the limitation, right? Well, that's also a limitation for the gasoline cars, but guess what? You stop for the gas, how long does it take you to put the gas in the tank? 2 minutes, right? That's it. How long does it take you to charge the battery? Longer, right? So these trucks apparently can go 300 to 500 miles on one charge, which is actually pretty darn good, right? Anyhow, substantial part of what these trucks involve, like autopilot, is something that's a buzzword these days, right? What does it stand for? AI. Artificial intelligence, right? Artificial intelligence. And there is a lot of buzz around artificial intelligence, right? Robots are going to replace humans in a lot of jobs, right? That is true, by the way. This truck probably is the first step to replacing truckers, right? And truckers is a fairly popular profession, actually, right? It's fairly well paid as well, but it's a hard job, obviously, right? Can you imagine sitting on your butt like 8 hours a day just driving? At some point, you're going to start hating your life, right? So yeah. Even though the money is good, you can't do it forever, right? Okay, so what in the hell is artificial intelligence? Well, this is actually not a new area, I got to tell you. It received a lot of attention, especially lately, because all of a sudden we found applications. But artificial intelligence existed probably, the idea of artificial intelligence existed probably since, I'd say, 1970s, okay? It's not a new concept. The reason why it became so popular these days is because we have powerful computers with a lot of firepower that can run a lot of computations, that have gigantic memory and fast processors. Okay, that's why artificial intelligence became possible. Okay, now artificial intelligence actually is modeled after the brain, after the human. It's an attempt to model human brain. Essentially, that's what it is. Okay, now I don't know if you took the bio in high school, but what's inside our brain? What is it composed of? What are the cells of the brain called? Neurons, right? Our brain it consists of neurons. Neurons, okay? And each neuron looks like that. So there is a cell core, right? And then there is a cell body around that. And it has a bunch of kind of really long legs growing out of each cell, right? So on one end you have this kind of thing, this type of structure, okay? And then also it can go this way, and then there is something like that. So this part of the neuron is called, I believe, Dendritic Tree. So there are dendrons and axons, right? So these are dendrons. Okay, and there is one single axon going out. This is called axon. Okay? So here is how the brain works, apparently. Okay? This is how God created our brain. What happens is the dendrons are in contact with axons of other neural cells. Okay, so for example, there is an axon from another cell that goes right here and almost touches this dendron right here. Okay, then there is another axon coming right here, and it almost touches this dendron as well. Okay, so these points essentially is where cells interact with each other. Okay, I believe it's called synapse, right? So there is it's like incoming neuron right there. So there is an area between, right? And there is an outgoing neuron after that. So this space is called synapse. And what happens is when this dendron receives a signal incoming from this axon, okay, it basically carries this signal to the nucleus of the cell, all right? And there may be some other signals also carried from other parts of the neuron. So they all converge together. All these signals converge together in the center of the cell. And after that, the neuron, the cell of the brain, basically sends the signal over here. Okay, so the signal propagates, and by the way, it also ends up in this ending, the neuron ending, which meets another dendron right here. And if the signal makes it through, then the signal goes to another cell, right? That's how cells communicate in our brain, essentially. So all our brain does really is sending signals from one cell to another cell. And multiple signals converge, and then it creates the output. Okay, that's basically how our brain works. You know how many cells do we have in the brain? Order of magnitude, of course, right? Nobody knows the exact count, and probably it's different from person to person, right? But approximately our brain contains 10 to the 10th power cells. Okay? It's enormous amount of cells. But here is the kicker, okay? Here is what we discovered, apparently. When the signals, let me use another color, okay? Let me use green, for example, right? When the signals converge into the cell nucleus, it does not necessarily create the outgoing signal. That's the thing, okay? In other words, our brains are non-linear. It's not like it's just basically getting the signals together, adding them up, and sending the same sum along the axon, okay? In order for the axon to receive and conduct the signal, the sum of the signals should exceed a certain threshold. It's not, in other words, brain, amazingly enough, operates by the schema all or nothing kind of thing, okay? In other words, let's say that this is my nucleus, right? And here is the signal number 1 coming in, here is signal number 2 coming in, here is signal number 3 coming in. And what happens is, if the sum of these signals does not exceed certain threshold, let me call it threshold right here, okay, then the outgoing signal is going to be 0, nothing, okay? So signals coming in, they converge together, but it does not create any output. It just doesn't break the ceiling, so to speak. But once the sum of the signals exceeds this threshold, all of a sudden, bam, there is a signal coming out, okay? So that's how brain operates. It's either 0 up until certain limit, or after that it's, yes, there is a signal coming through. So I'm going to send signal to the next cell. That's how our brains operate, okay? And after that, of course, let me go back to the previous, right? So there is a signal coming from one of the cells to another, right? Then there is another axon, and the next cell does the same thing, right? It receives multiple signals from whoever is in contact with this cell, and it adds them together, and again, same thing happens. If the certain threshold is exceeded, it sends the signal forward. So our brain essentially is just an electrical circuit, okay, of cells that send each other electrical signals, and they either pass it forward if they exceed certain threshold, or they don't pass it forward. Okay? That's how the brain operates. That comes from the area, of course, of biology, right? Neurobiology, okay? And by the way, we as a humanity, we didn't even scratch the surface, okay? Essentially what I'm saying is, we don't know crap about how the brain operates, really. So this is just, we're at the beginning stage of understanding what happens inside the brain. In 80% of the cases, we don't know the answer, what happens inside of the brain, okay? Why is that happening? Why doesn't just it send the signal forward? What's the mechanism? What's the chemical mechanism? Nobody knows, really, okay? That's unfortunate, but that's where we stand. And basically, what artificial intelligence is, it's exactly creating same model, okay? Let me kind of show you. What we can do is this. Let's say that I'm going to model brain in this form, okay? That's going to be like a cell, right? And cells can receive signals, right? So I'm going to assume that each one of these cells receives one signal. After that, I'm going to have another layer of cells, and these cells receive signal from the previous layer, right? So, for example, cell number 1, 2, and 3. Each one of them can send a signal to cells 4, 5, and 6. In other words, one can send signal to 4, and it may be connected to 5, and it may be connected to 6. 2 is connected to 4, 5, and 6. 3 is connected to 4, 5, and 6. And after that, all of them can send the signal to another cell, number 7. So 4, 5, and 6 send the signal to 7. And 7 basically responds, right? It will either send the signal forward or not, depending on how strong is the combination of inputs, right? And that's it. That's how essentially neural net works, okay? It's basically signals being sent from one cell to another cell, and they're either being passed forward or not. All right? To a large extent, this is a black box model. All right? Let me give you some examples of like when can we find applications of artificial intelligence in the real life. I'm sure all of you have cell phones, right? When you take a picture of a group of people, do you see like yellow squares around faces, right? So the phone software tells you, this image that I'm about to capture, it looks like this spot right here is a face, this spot right here is a face, and this spot right here is a face, right? How can it do it? Image recognition, okay? So it's done by the artificial intelligence. There is a program behind the scenes that basically analyzes the image pixel by pixel and says, this cluster of points looks like a face, okay? Speech recognition. How many of you have iPhone? How many of you talk to Siri every once in a while? Hey Siri, what's the weather out like? How Siri understands your voice? It's artificial intelligence. It's a mathematical model that was trained to understand the electrical signals that represent voice, break them into the parts and pieces, and create like words, recognize words out of that. Okay? So artificial intelligence is, a lot of that is around us, a lot of that is commercial already, okay? But at the same time, there is a lot of research that's going on. So as we speak, this is a quickly developing area right now, okay? And that's why a lot of companies invest, because, like I said, artificial intelligence was just a cute model. Let's do this kind of model right here, okay, to model how the human brain works. It was nothing more than a cute academic exercise. And only a few years ago, I believe I read about that, in 2012 or something like that, there was a data scientist from Toronto, Canada, who actually presented an algorithm that was able to identify parts of the image. So it's a program, and you send the program an image, a file that contains a picture, right? And the file, may, for example, it can contain a big picture of ship, okay, on the water, everything. So it's a real image, real picture taken with the camera, right? And then after that, the program basically says, well, with the likelihood of 70%, this is a container ship. With the likelihood of 30%, this is a, scooter. And with the likelihood of like 10%, this is a car. So it can identify the boat, can identify the cat, for example, etc. Okay, and that was so unusual. So we as a humanity didn't know that it was possible. And after that, people realized that, hey, neural networks. This is called neural network, by the way. AI, artificial intelligence. Another name for that is neural network. Now you know why, right? Because it models the network of neurons in the brain. That's what it is, right? So after that, we as a community realized, oh my God, that can be used to other applications. And then right now we're standing kind of in the middle of this revolution where companies investing millions and even billions of dollars to develop applications for artificial intelligence. So this is a hot area right now, okay? But I believe we're out of time, right? Okay, let's stop it right here. And on Monday,